In this video, we will continue with Chapter 10 on exponential and logarithmic functions, and specifically focus on section 10.3 to 10.5, which is on logarithms. So section 10.3 on logarithms. What is the meaning of the logarithm? Say, for example, we have log 4, 60. This will be equal to 2. How does this relate to the exponential factors that we have been looking at? 4 squared is equal to 16. So we have 16, we have 2, and we have a 4. So our log base is the same as our exponential base. The answer of our log is our exponent, and the log value is our answer to the log value is equal to the answer of the exponent. So what do we have? We have y equal to b to the power of t is the same as log with a base value of b. Y is our answer, and this will be equal to t. So if t is our unknown, this is how we will solve our exponents. There are two logs, so log 10 is usually is useful for round values. So log 10 of 1,000 is equal to 3. Log base 10 of 100 is equal to 2. Log base 10 of 10 is equal to 1. Log base 10 of 10 is equal to log base 10 of 1 is equal to 0. Log base 10 of 0.1 is minus 1, and log base 10 of 0.01 is equal to minus 2. Remember, our preferred base b is equal to e. So if we have log base e, this is called, or we write that as Ln, which is the natural logarithm. This is what we will use in most of this course. There is also a function on most calculators. So why is this important? So if we have y equal to e to the power of t, this is the same as t equal to log of y. Some rules of the logarithms. So first, the log of a product is equal to the sum of the logs. The log of a fraction is the difference between the logs. The log of an exponent is bring the exponent down, log u. So just to make that clear, log bu is the same as two natural logs. So it's the same as log b of e times the log e of u. And 5 log b of e is equal to 1 over log e of b. Section 10.4 logarithmic functions is self-study. The most important part of this is base conversion, which is section 10.4. I will show this in an example in a second video. Finally, section 10.5, derivatives of exponents. So first, the derivative of the exponent we've already have, it's simply the exponent. The derivative of the natural log is 1 over t. So if we generalize these function, the derivative of e to a function of f of t, remember we need the chain rule, so it will be f prime t of et and d over dt of log of f of t will be equal to the derivative over the function. So please remember to study these so that you remember them in case. Also look at the examples in the textbook. So finally, we need to look at instantaneous rate of growth. So before we had V, A, R, and T. So V was our value of our investment, E was the initial state, this was the interest rate, and T was the time invested, for example. So if we take V equal to our approximation, if it's continuously compounded, then we have V equal to AERT. Let's take the derivative of V with regards to T. We know this is ARERT or equal to RAE A to the power ERT is V. So we have the derivative is equal to RV. So this derivative gives us the rate of change at a specific point in time, t. The rate of growth or the instantaneous shouldn't be an E. Instantaneous rate of growth must be expressed as a ratio of the initial value, or of the total value. What does that mean? Our instantaneous rate of growth is equal to the rate of change expressed as a ratio to the overall. That means RV over V is equal to R. So our instantaneous rate of growth is equal to R. In the next video, we will look at the optimal timing strategy as well as this growth rate.